Hello, and so we are doing graphing for acceleration. Now we have this word problem here and three graphs. One's velocity, one's acceleration, and one is distance graph. So for our word problem, we have the title, quick graphs, and then we have the word problem. A runner with an initial velocity of -2 meters a second accelerates by 1 meters a second for 2 seconds before lunging forward, instantly accelerating 2 meters a second, keeping that velocity for 2 seconds before decelerating at a rate of -1 meters a second for 2 seconds. Graph the sprinter. Now, this word problem is a big chunky one, so you might want to pause the video and break it up, so you should probably do that. But now I'm going to continue on and show you how to break it up, how I break it up at least. A runner with an initial velocity. This means that your runner is going to have a v0 of -2 meters a second. Accelerates by 1 meters a second for 2 seconds. So one of your accelerations here is going to be a1 equals 1 meters a second. I'm going to get rid of that very ugly 1 meters a second. And then he says, before lunging forward, instantly. Now this is very important. Instantly accelerating 2 meters a second, meaning that there is no acceleration here. It instantly jumps from whatever this value is at whatever it ends at to by 2 meters a second. So you add 2 meters a second on top of whatever this ends up being. So that's important to keep in mind. Keeping that velocity for 2 seconds, meaning that for a little bit, your velocity is a constant for 2 seconds after you've added that instant acceleration of 2 meters a second, before decelerating at a rate of -1 meters a second for 2 seconds, meaning that your A2 is going to be -1 meters a second squared. Both of these are squared, I forgot about that. Anyways, you're going to want to graph this. This is the information you have very easily. Your v0, which is -2, this is where you start at. Your acceleration for 2 seconds, which is 1 meters a second squared. And then your second acceleration, which is a deceleration of -1 meters a second squared. And of course, you have your instant acceleration at 2 meters a second, and how long they keep these two values. 2 seconds for the first acceleration, and 2 seconds for the keeping the velocity, and another 2 seconds for the second acceleration. So you might end up where, you might see already where this is ending up, but I'm just going to explain it anyway. V0 here, 2 meters a second, right? So we know A1 equals 1 meters a second squared. And we know it's going to keep that value for 2 seconds, meaning that this ends up being a total velocity change, a change in velocity of 2 meters a second. A total change in velocity of 2 meters a second. Now, because we accelerated from this space point, we just add this together, meaning that our v1 after we've added v0 and v1 together, our v1 equals 0 meters a second. And then you have the instant acceleration here by 2 meters a second squared. It doesn't really matter here, but you instantly accelerated, so you basically just add 2 meters a second here. That's pretty much it. You just add the 2 meters a second, and then so your v2 equals 2 meters a second. Simple, right? And then it holds this for 2 seconds, important to take note of. And then it decelerates, deceleration here, up here, if you notice, at a rate of -1 meters a second for 2 seconds, meaning that your A2 is going to be multiplied by 2 seconds, equaling -2 meters a second change in velocity. So then you just take V2, add it to A2, so V2 plus A2 equals -2, wait, I'm dumb, 0 meters a second. Now the 0 makes it easy because we're just simply going to end off at 0. So now we have these values. And so we can plot this on our velocity graph. Now over here. Over here is our velocity graph. And it's all scaled by 1, so you can count the squares here. But we're going to start here, because we start, if you look at this, our v0 is negative 2 meters a second. Negative 2 meters a second means that if we start here, and after 2 seconds, we end at 0. 2 seconds, we end at 0, right here. And then we instantly accelerate by 2, which means in an instant, we don't even go over a space. In an instant, we are now here. And then we continue that speed for 2 seconds, meaning that we also end up here. And then we decelerate at a rate of -1 for 2 seconds, meaning after 2 seconds, we end up here. I think you can see how to graph this. Because this is velocity, we graph all straight lines. Velocity there, dotted line here to represent the instant acceleration, another straight line across, and another straight line down. That is your velocity graph. Velocity is meters a second in seconds. Simple, right? Now, for your acceleration graph. The acceleration graph is meters a second squared for the y-axis and seconds for the x-axis. But here, we go off of the acceleration between different points. Between this point and this point, it's accelerating over 2 seconds by 1 meters a second, meaning that here, we accelerate at 1 meters a second. This is 1 for 2 seconds. And then we instantly jump. And now that might have you thinking, oh, we're going to place it all the way up here. But no, we're not. Because you instantly jump, you're not actually accelerating for that time. You instantly jump to that speed. And then you're keeping, for the intervals between this point and this point, a constant speed. Meaning that you're going to make a line from here to here. I made it off of the x-axis. It's technically supposed to be on it. There is no acceleration here. But just so you can see it, I made it off the x-axis. And then you notice we are decelerating from this point, from this time onwards. We're decelerating by a rate of 1 meters a second for 2 seconds, meaning that we simply go down here and draw a line to symbolize our deceleration. This is -1. So to translate this graph from here, you are simply taking the interval of the slope. You're taking the slope between the two points, and you're simply just converting that into this. So the slope of this is 1. So you're going to convert it right here. You're going to put a straight line on 1. Y equals 1, which is this, for 2 seconds, which is why it cuts off here. For this one, the slope is 0. The slope is 0. So you put it at y equals 0 for 2 seconds. And for this one, the slope is -1. And so you're going to put it at -1 for 2 seconds. I hope that makes sense. Now we're going to convert this graph over here to the distance graph, which is simply meters and seconds. Now, meters and seconds are the term. Converting this to this is a bit confusing at first, but all you need to know is that critically, these integrals matter. You simply divide the points you simply chunk them out between the points, and you take the integral of this graph. So right here, this is -2 and 2, right here. The sides of this are -2 and 2. So we're going to take the integral, which is multiplying these two things together to find the area basically under this line, between this and the x-axis. So what that would be 2 times -2, -4 divided by 2, which would mean this is -2. Now, what does this matter? This integral value here, we take, and we simply go over down here and say, at 2 seconds, this is what matters. From this point to this point, you only take this point. At 2 seconds, this value, right down here, will be -2 at 2 seconds. That's what this matters. This determines your y value. The integral determines your y value on this graph. And whatever point it ends at determines the x value. These are coordinates. You simply graph these points. Now, we see here that the integral here is 2 times 2, which is +4. That's simple, right? The integral is +4. Now, if we go over here, we go +4, we notice that it ends right here. So at 4 seconds, we will add on top of this point +4. 1, 2, 3, 4. +4. Up here. It is 4 higher than the point it was. That's what matters. The reason this is -2, and that's not just +4, is because we started at the origin. And so we subtracted 2 from there, and now we're adding 4 from this point to go up to this point. That's how that works. And from here, we have another integral, which is just 2 and 2. So we get 4 and 2 inside, +2. Meaning that if we take this value +2 and we go down here at 6 seconds, which is where this ends, at 6 seconds right here, we will add another +2 on top of this. So how do we then make the lines? Well, if you're looking at this, you'll see that this is an acceleration. This is a constant, and this is a deceleration. This matters. Watch. So, because we are accelerating here, we have to curve it. We are curving. Because this is a negative, but this is important. If you start at a negative or positive value for your velocity, like a strong negative, when you are leading this graph, you will have to go down. You will have to go down and curve it that way. This is because when you are going down, this is the slope here symbolizes velocity. The velocity of this graph is nearing 0, meaning that the slope of this is nearing 0. It is slowing down. If you look at this, this graph is decreasing in slope, so it will near 0. Then you look up here. This is an instant acceleration, meaning that from this point to this point, there is no curve, meaning that this is a perfectly straight line. Okay, that's not very perfect, but it's good enough. A straight line. Now from here to here, what does this mean? This is deceleration. This graph is decelerating, meaning that it will near 0. So because it is strong, you lead upwards. It already has a positive velocity. You lead upwards and you curve into it as it goes to 0. Now we can't graph beyond this because we don't have any more values beyond this. So this is your graph for your meters traveled. I hope that helps. If it doesn't, ask me. But if it does, congratulations. You got a hold of velocity and acceleration graphs. Keep it up.